phase and group velocity. So what we are discussing is about de Broglie waves, and it is nothing but matter waves, right? That is, if you are running with a very high speed, then there will be a wavelength associated with you, that is h by p. But the problem is, here you know the value of h, that is 6.626 into 10 raised to minus 34 meter square kilogram per second divided by p, that is mass into velocity. So suppose your mass is 70 kg and you are driving a supercar, so you are traveling at a speed of 300 km per hour. Okay, so you can calculate the associated wavelength with you, and you can see this is a very small value, right? That is the wave nature associated with you, or de Broglie wave associated with you is negligible. But if the moving particle is electron or something, then we know its mass is 9.1 into 10 raised to minus 31 kg. So by substituting this value here, you get the value of associated de Broglie wavelength with the moving electron. So that value is not negligible. So in classical mechanics, we can consider the electron as a particle with certain mass and it is moving with certain velocity. But when we are coming to quantum mechanics, in quantum mechanics we consider it as a wave, because if it is moving with a high velocity, then the wave nature will dominate. So in quantum mechanics we see this particle motion as a motion of wave packet. So wave packet means it consists of large number of waves of slightly different wavelength, like this, and the envelope of all the waves having slightly different wavelength is called wave packet. So this is the wave packet, and I told you it consists of different waves of slightly different wavelength. So where the particle is present, all these waves will constructively interfere. That is, here it is constructively interfered. All the waves constructively interfere. So we can see the wave packet, and where the particle is not present, that is this position and this position, where these waves will destructively interfere. And the velocity of this wave packet is called group velocity, Vg, and velocity of individual waves inside the wave packet is called phase velocities, that is Vp. And I tell you one more thing. From this idea only the uncertainty principle arises. How? See, in the classical mechanics, the position of the particle is determined. We can say if it is x-axis, then I can say the particle is at this position. But here, in this case, you see, the particle is spread over the wave packet. So I can say the particle is here. I can say particle is here, but particle is spreaded over this wave packet. So what I can say is, I can say the particle is present in between this distance that we called delta x. And within this distance, I can say the probability of finding the particle at this position and probability of finding the particle at this position. Okay, so this is the basics of uncertainty principle, delta x, delta px, right? Okay, we will discuss all those things later. Okay. So under this section, the phase and group velocity, my question is this Vg is equal to Vp? Is it always Vg is equal to Vp? No. There are different cases. So we will discuss what is the different cases for Vg and Vp. I show you one video. There you can see the group of fishes moving with a certain velocity, but inside that group, each of the fish is moving with a different velocities. That is the phase velocity. That is the velocity of individual fish is phase velocity, and the velocity of entire group is group velocity. So generally Vp is not equal to Vg. Now we want to derive the equation for group velocity and phase velocity. To derive it, we need to know a little bit about wave propagation. Suppose we are taking a string, and in a string, if we disturb the string, the wave will propagate like this. Okay. So this is our x-axis, and the wave propagation is dependent on time, and this is our y-axis, and in y-axis we can see the particle propagation. So this way we can mathematically represent as y is a function of x and t. So we can represent the position of particle at each time and each position. And more generally, we can derive an expression for this one, that is a e raised to I kx plus or minus omega t. Why this plus or minus? Because sometimes maybe the wave is propagating in the forward direction, or it may be propagating in the backward direction. I will tell you how we can find out the direction of the wave based on these signs. Okay, later I will discuss those things. Okay, now I am going to derive the equation for phase velocity. What we have to derive? We have to derive the phase velocity. That is, we have to take this phase. This is the phase of a wave propagation. Okay, so we know kx plus or minus omega t is phase. And for a wave, it will be a constant value. So I can write kx plus or minus omega t is equal to some constant c. And I can rearrange this equation, that is kx is equal to c minus plus omega t. Now I am going to take its derivative with respect to time t. So I get k dx by dt is equal to minus or plus omega. So I can rearrange this equation, that is dx by dt is equal to minus or plus omega by k. See, dx by dt, there is nothing but velocity, and here we derive this value from phase of the wave. So it is nothing but phase velocity Vp, that is minus or plus omega by k. So this is the equation for phase velocity. That is Vp equal to minus or plus omega by k, where omega is angular frequency and k is the propagation constant. And the group velocity is defined as, that is Vg is equal to d omega by dk. So in the case of a wave packet, this is the each waves with a different wavelength, and the velocity of this waves is called Vp, that is omega by k, and the velocity of the entire group, that is the velocity of this envelope, is called group velocity Vg, that is d omega by dk. That is, phase velocity is velocity of the individual waves in the wave packet. Dispersion relation. We know phase velocity Vp is equal to omega by k, and we know group velocity Vg is equal to d omega by dk. So from this equation, I can rewrite and I can find out an equation for omega that is equal to Vp into k. Now I am modifying this equation by substituting this omega value here, that is Vg is equal to d by dk of Vp into k. So what we get? We get Vg is equal to derivative of Vp, that is dVp by dk into k plus Vp. And I told you here this k is nothing but 2 pi by lambda. So from this relation we can find out the dk value, that is dk will be equal to minus 2 pi by lambda square into d lambda. Now I am going to substitute these two values in this equation. So what we get? We get Vg is equal to dVp by dk, that is minus lambda square by 2 pi d lambda into k is 2 pi by lambda plus Vp. So we can cancel this 2 pi and lambda square and lambda. So we get Vg is equal to Vp minus lambda dVp by d lambda. So this relation is called dispersion relation. Maybe you have a doubt. What is all these things? What is its physical significance? I tell you. To explain this idea, we have to go to our school level experiment. The experiment with the prism. Let us consider a prism. I know everyone is very familiar with the prism experiment. It is a school level experiment. A white light is falling on this prism. Then what will happen? Inside the prism, it will split into different colors and we get the rainbow. And we call this phenomena as dispersion. Right? So from this idea itself, the name came, that is dispersion relation. See, these are waves of different wavelength, lambda 1, lambda 2, lambda 3. And this white light consists of all this wavelength. Right? So when it is passing through a medium, it is separated into different colors. How it is happening? You just look into the above equation, that is Vg equal to Vp minus lambda dVp by d lambda, where each of this wavelength travels with a different velocity. That is phase velocity of each of this wavelength is different through the medium. See, this white light consists of all this wavelength, right? And when it is traveling through the air or vacuum, this Vg will be equal to Vp. So each of these waves also travels at the same velocity as the group velocity. Okay, but when it travels through the medium, so this is our medium, each wavelength will travel with the different velocities. So Vp1, Vp2, Vp3, etc. That is inside the media, this value dVp by d lambda will not be equal to 0, but when it travels through this air, dVp by d lambda will be equal to 0. So this is the dispersion relation. That is, in a non-dispersive media, dVp by d lambda will be equal to 0, and when it is in a dispersive media, dVp by d lambda will be not equal to 0. So in a non-dispersive media, Vg will be Vp, and in a dispersive media, Vg is equal to Vp minus lambda dVp by d lambda. This is the dispersion relation. So Vg is equal to Vp minus lambda dVp by d lambda. This is our dispersion relation. And in a dispersive media, I told you dVp by d lambda will be not equal to 0. And not equal to 0 means maybe it is positive or it may be negative. That is, Vg is equal to Vp minus lambda dVp by d lambda, or Vg is equal to Vp plus lambda dVp by d lambda. Here you can see this Vg value is less than Vp, and here you can see this Vg value is greater than Vp. That is, here individual waves travels a higher velocity, okay, and group will follow it. And here group will travels with the higher velocity and the individual waves travel with the lower velocity. In all the usual cases, Vg will be less than Vp. So we call this as normal dispersion. And in some very anomalous cases, the group will travel higher velocity than the individual waves. So it is called anomalous dispersion. Vg and Vp in terms of energy and the momentum. So we know the equation for Vp, that is equal to omega by k, and we know Vg is equal to d omega by dk. Now we have to find out the corresponding relation in terms of E and P. That is, Vp is equal to omega by k, right? Here I am multiplying with h cross and dividing by h cross. So this is h cross omega. H cross omega is nothing but energy E, and h cut k is nothing but momentum P. So we got relation for Vp, that is equal to E by P. And similar to d omega by dk, we get Vg is equal to dE by dP. And I can tell you one more equation for Vg, that is, we know Vg is equal to d omega by dk, where we know omega is equal to 2 pi nu by k is we know d 2 pi by lambda. So what we get? 2 pi will cancels, and we get d nu by derivative of 1 by lambda, that is minus lambda square by d lambda. So this is another expression for Vg, that is equal to minus lambda square d nu by d lambda. Some special cases. First one is free particle. So we want to find out the Vp and Vg of a free particle. I told you what is the meaning of free particle. That is, potential will be equal to 0. Therefore, we know the total energy E is equal to kinetic energy plus potential energy. But for the free particle, potential energy is 0. Therefore, here energy is equal to kinetic energy. And we know the kinetic energy is equal to p square by 2m. Now we have to find out the phase velocity, that is Vp, that is equal to, in terms of E and P, it is E by P. So here we know the E value, that is p square by 2m by P, that is we get P by 2m. And now we have to find out Vg, that is Vg is equal to dE by dP. So we have to take derivative of energy with respect to P. So what we get? We get 2P by 2m, that is P by m. So for free particle, Vp is equal to P by 2m and Vg is equal to P by m. So I can make the relation between Vg and Vp, that is Vg is equal to 2 Vp. Second case of a relativistic particle. For a relativistic particle, we know energy E square is equal to rest mass energy E0 square plus P square C square. So we can find out E is equal to root of E0 square plus P square C square. Now, what is our relation for Vp? That is E by P. That is, this is equal to root of E0 square plus P square C square by P. Now, what is Vg? Which is dE by dP. So we have to take derivative of energy with respect to P. So what we get? We get 1 by 2 into E0 square plus P square C square all raised to minus 1 by 2 into derivative of this term, that is 2P C square. So we can cancel this 2 and remaining we get this is equal to P C square by root of E0 square plus P square C square. So we got a relation for Vp and Vg. Now I am going to multiply this Vp with the Vg. Then what we get? We get root of E0 square plus P square C square by P into P C square by root of E0 square plus P square C square. So what we get? We get it is equal to C square. That is, product of Vg and Vp for a relativistic particle will be equal to C square. Examples. First one, Vp is given, that is Vp is equal to root of g lambda by 2 pi. The question is to find Vg. We know Vg is equal to d omega by dk, right? So what we have to do? We have to find out the relation for omega from this equation in terms of k. Then only we can take this derivative. Okay, so how we can solve? You know, Vp is equal to omega by k, right? And that is equal to root of g lambda by 2 pi. Where we know 2 pi by lambda is nothing but k. So we can rewrite this equation, that is omega by k is equal to root g by k. Now we can find out the relation for omega, that is omega is equal to root g by k into k. That is, we get omega is equal to root gk. So we got equation for omega in terms of k. Now what we have to do? We have to take derivative, that is d omega by dk. That is equal to 1 by 2 gk raised to minus 1 by 2 into derivative of this terms gk, that is g. So what we get? We get d omega by dk is equal to 1 by 2 root of g by k. Example 2. Frequency nu is given, that is equal to 2 pi t by rho lambda cube. The question is to find Vg. So we know for Vg there are different equations. One is Vg is equal to d omega by dk, and another equation is Vg is equal to minus lambda square d nu by d lambda, and Vg is equal to d e by dp. So which equation is suitable here? Second one, right? So because nu is given and it is a function of lambda, right? So we can use this equation, that is we get Vg equal to minus lambda square d by d lambda of nu. Nu is root of 2 pi t by rho lambda cube. So what we get? We get this is equal to minus lambda square into 1 by 2 into derivative of this function is rho lambda cube by 2 pi t into derivative of this entire time with respect to lambda cube. So what we get? 2 pi t by rho into minus 3 by lambda raised to 4. So you just cancel out the term and find out the final value for Vg. So work for you, okay? Some works for you. Frequency nu is equal to root g by 2 pi lambda. You have to find out Vg. Here in this question, the dispersion relation is given, that is omega square of k is equal to omega 0 square into 3 minus cos kxa minus cos kya minus cos kza. And they're asked to find out the velocity of phonons at large wavelength. See, lambda is large, that is it is tending to infinite value. So what will be the k value? We know k is equal to 2 pi by lambda. So when lambda tends to infinity, what happens? K tends to 0. That is cos k, cos of the angle, that is kxa or kya or kza is tending to 0. That is, we know when theta is tends to 0, for sin theta, we know it is approximately equal to theta, and for cos theta, it will be approximately equal to 1 minus theta square by 2. So we know this idea. So what happens? This cos value will be 10 to 1 minus theta square by 2. Here the theta is k x square a square by 2. Here this cos value will tend to 1 minus k y square a square by 2, and this value tend to 1 minus k z square a square by 2. So substituting these values here, we get omega square of k is equal to omega 0 square. So here 3 minus 1 minus 1 minus 1, so that 3 will cancels. So the remaining we get a square by 2 into kx square plus ky square plus kz square, where kx square plus ky square plus kz square is nothing but k vector, right? So that is omega square k we obtained as omega square a square by 2 into k. That is, we get omega of k is equal to omega 0 a by root 2 into k. That is, here it is k square, right? So what we have to find out? We have to find out the velocity. What is velocity? That is, we know Vg is equal to d omega by dk. So from this equation, what we get? We get omega 0 a by root 2. That is, option D is the correct. This is a very simple question. I think you got the answer, right? For anomalous dispersion, the condition is Vg is greater than Vp. So the group travels at a higher velocity than its individual waves. Okay, this is very anomalous behavior. It's not a common thing. It's a very anomalous. That is why it's calling anomalous dispersion.